Hello and welcome to our video on performance. R gets kind of a bad rap in that people think it's a slow language, and there are some aspects of R that are slow, but I think this reputation is a little bit unfounded. And we're going to talk about ways to write R code that does run fast and some general things to look out for. But then we're going to spend most of the time looking at an example and diving deep into different algorithms for computing something. Okay, let's get started. So just a few comments here at the top. If you want to write fast code that does things faster, you really need to be able to measure it, measure how fast various parts of the code take and how much resources are being used. And your general strategy for making your scripts or functions run faster should be to measure, find out what the slow parts are, determine whether they can be improved, and if you think so, then try to improve them, and then measure it again, and then if there's something else that sticks out as a slow part or bottleneck, go in and fix that. While you're doing this, it's important to also be able to test that the new code gives the same answer as the old code. So it's good to put your code in functions and then call one function, get an answer, call your revised function, get an answer, and check that they're actually the same answer as you're tinkering with the new version. So let's start with just some general advice. There aren't going to be many things here, but I think these are some good things to remember as you're trying to figure out where the bottlenecks are. So the first thing is that these quote-unquote vectorized functions are faster. As an example, let's look at the problem of raising the elements of a vector to, or taking the exponential of elements of vectors, to say basically e to the x. So I'm just going to generate, let's see, 10 million random normals. And there's a handy function called proc.time. You'll see what that does in just a second. Basically, this records the current time. And then we're going to calculate something. So we're going to initialize a vector y. That's the same length as our input vector x and just has NAs in it. And then we're going to do a for loop over 1 to the length of x. And each iteration of the for loop, we're going to do e to the x of j and assign that to y of j. And then when we're done, we're going to record the time. So let's run that. And let's look at t2 minus t1. This took about 1 second. And let's look at another method for doing this. This is the vectorized version. Basically, the function exp, which we're calling up here, can not only raise a single element of the vector to e to the x, you can basically give it the whole vector and it will do e to each element of the vector. So that's that. And then, so I'm going to run this all together. Basically, what we're going to do is start the timer here, do this part, record the time here, do this part, and then stop it. So basically, this minus this is going to be the time for that, and this minus this is the time for this part. Okay, and let's print the results. The first one with the loop took 0.946 seconds, and the second one in the vectorized version took 0.145 seconds. 0.946 divided by 0.145 is about 6.5 times faster. So these numbers are something people typically look at to measure how much faster a piece of code is. This is the amount of speed up this vectorized version gives. Okay, let's look at another very important principle. What we did up here is we used the rep function to initialize a vector y, which just had NAs in it. A somewhat common way to do things would be to do it like we do down here, where basically I initialize y to be just a vector of length 0, And then in the loop, I would just append the next value in here. It turns out this sort of operation is very inefficient compared to filling in an already existing vector in R. So let's run this and you can see why. So here we're going to do, all right, just to remind you how long things took. When we did 10 million entries, this took about 1 second when we initialized the vector. We're going to do 100 times less, so 100,000 entries. And we're going to do it this way. Boom, 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 boom. This is already taking much longer, even though it's a problem that's 100 times smaller. And it took about 8.7 times longer. So this is extremely inefficient to just append things and make this vector y grow as you go. The same idea applies to using rbind and cbind. Rbind is used to bind either matrices or data frames together by binding, top to bottom. Cbind is used for binding things left to right, column bind versus row bind. So it's almost always better to just basically initialize either a vector or a matrix with missing values and then fill it up as you go, as opposed to building it up as you go. So that's generally going to be much more efficient. Okay, the next idea is you should use the right type of object for the job. So in one of our very early videos, we looked at various different types of R objects. And basically what I mean by using the right object for the job is you should use the simplest possible object that has the flexibility and capabilities that you need to solve your problem. So let's look at an example here. We're going to compare using a matrix versus using a data frame. And the operation we're going to do is we're going to pick, okay, let me create these first so you can see what we're looking at. Basically, I'm just filling in an 8,000 by 8,000 matrix with random normals. So dim x 8,000 by 8,000. And then D is just, it's the same information as x, but I'm converting it to be a data frame. So it's all the same. And basically what we're going to do is pick 10,000 random entries of this gigantic matrix. By the way, the matrix has 8,000 squared, 64 million entries. So we're going to take 10,000 of those entries selected randomly and do E to the entry and assign it. There's no real reason to do this, but this is just to show the difference between using these two different objects. So we're going to do it here using the matrix, and we're going to use it here doing the data frame, and we're going to time it all. You could see that the matrix version took about half a second, and the data frame version took more than 2.5 seconds, so more than 5 times slower using a data frame. So the reason is that a data frame is it's a more complicated object than a matrix. A matrix is basically just an atomic vector with a dim attribute, whereas a data frame is it's kind of like a list with the property that each list element has the same length, and each list element is a vector of the same length. So that object is really just not the right object. It has too many features relative to the sort of minimally complicated object that you really need for this problem. So the message here is use the right object for the job, which means use the simplest possible object. And lists and data frames tend to be slower to operate on than atomic vectors and matrices. Okay, you may have heard at some point that if your loop is slow, you should use one of the apply functions to make it run faster. This can sometimes be true, but I've found that more often than not, there's a better way to do it. So the message here, apply isn't perfect. Use built-in functions when possible. So this is sort of the same idea previously. So previously we said use the right object for the job, which really means use the simplest possible object. Here we're saying use the right function for the job, as opposed to, the most generic function like apply, which allows you to basically apply any function along one of the dimensions of x, as opposed to a specific function which does exactly what you want it to do. So in this case, what we want to do is sum up the columns of this matrix X. So one way to do it is with the apply function. So apply X to sum means apply the sum function looping over the second dimension, which is the columns of X. So that will do that. But there's also a built-in function called callSums, which does exactly that and is designed to be very fast. So if we do this and make the comparison, you can see that there's really no comparison. It's how many times faster? 13 times faster to use callSums. So similar idea, use the right function for the job, just like you should use the right object for the job. Okay, now what we're going to do for the rest of the video is work on a specific problem and look at various different ways of coding it, different algorithms for solving the problem, and learn some lessons about how to make things run faster. Specifically, we're going to be looking at a function called profvis from the profvis library. So you should install that package if you don't already have it. So you would say install.packages profvis, and that will do it. I already have it installed, so I'm not going to run this. Okay. And we're going to be using the Hot 100 dataset, which is a dataset which contains information about the Billboard Hot 100 music chart going back many decades. So I'm going to read that in. And I'm going to do head to look at the dataset. So each row is a combination of a song and a week. And so it gives the chart position of that song on that week, the date of the chart, the song name, the performer, the song ID, which is basically they paste the song to the performer. There's a instance column, time on chart, how many weeks it's been on chart, consecutive weeks, so on and so forth. And then there's a URL. So the task here is we're going to quickly build a data set that has the URL for the first week each unique song appears on the chart. So basically, it's going to have a list of the unique songs, and then for each one, we're going to save the URL for the first time it appeared on the chart. Okay, so one thing you should try doing, so this is a big data set, so dim hot has 338,000 rows and 13 columns. So as you're testing things, it may be a good idea to work with a smaller data set, especially if things take a long time. Then you can kind of quickly figure out where the bottlenecks, and that process will be faster if you're working on a smaller data set. Now there's a danger that if the bottlenecks on a small data set may be different than the bottlenecks on a big data set. So it is important to also test the big data set as well. But for now, we're going to start with the small data set. And all of the methods we're going to be using to get the first URL for each song are in this function performancefunds.r. And so let me just pull that up here. And each method is called method. So first one's method 1, then we're going to have method 2 up to, I think, method 15. And these are in a function. It takes the data set as the argument, and then there's a method here. So let's just take a look at the first one. And this is kind of intended to be not very efficient so that we can improve upon it. So we're going to make mistakes relative to the things I just told you. So we're going to store all the unique song IDs in a vector and the first URL in the vector. At the end of the day, we're going to return those two things in a list. And so how this is going to work, we're going to loop over all the rows of the data set, grab the song ID for this row, and call it this song ID. And we're going to set inVector to false. And then we're going to loop over all of the existing unique song IDs. And we're going to check if any of them match this song ID. We'll switch inVector from false to true. And then when we're done with that, inVector is either going to be false or true. If it's already a song that's been accounted for, it's going to be true. And basically we skip this block. But if it's a song we haven't accounted for yet, then this not inVector, so inVector will be false, not inVector will be true. And then we're going to figure out the URL for the first time it appeared on the chart. So basically we have to look in the hot database for all the rows that match this song ID. So we're going to match song ID to this song ID. We're going to subset the data frame. We're going to find the minimum week in that data frame. So we're going to say which subhot.chartDate, so this is a smaller data set just for this song ID, matches the minimum of those. So that's the row that contains the minimum week. And then we'll update unique song IDs with this song ID. And then we'll update first URL with the chart URL for that row. And at the end of the day, we return everything. Okay, so that's what the code does. Let's run it. And we're going to time it just as we did before. And I think this one takes like 15 seconds or so. So we're just waiting. Okay, 18.9 seconds. Now, if that's all we have, then we're kind of in trouble. We don't know which parts are taking a long time. Luckily, this library called profvis will allow us to run the code, and it basically will measure things. It will try to figure out which parts of the code are taking the most time. So the way this works is you have to do library profvis after you install it. And then you wrap your code inside of a call to the profvis function. The profvis function takes an expression as its argument, and expressions are just code. And to get the best results, you should probably source the function as part of the expression, and then basically you just call the function. And then it gives you this really cool output. So this is again going to take 20 seconds or so. And then it brings up this really cool visualization of what's happening in the code. So this is what we called profvis blah blah blah, and you can see it didn't take any time on this step because the time is basically 0. It took 17.29 seconds because these are milliseconds on this part, and it used this much memory. Now down here, it's basically, this is a graph over time. And if I put my cursor over here, this is telling me, let me put it here actually, that this is, so up, I can't move my cursor and I can't point, but if you look at the top of the screen up here, that is matching with there. And then you can go like into the code. So basically if you go up from here, you're going into method 1. And the pink part moved down here, and you can see that inside of the method 1 function, this is the method 1 function, it's spending basically all of its time checking whether unique song IDs, basically checking whether this song ID was already accounted for. So one of the things you'll find, and basically this stuff takes no time compared to that. So basically, we've identified that this is taking way too long, and we need to focus on improving this part. Okay, so let's go back to our code. And basically, method 2 is going to improve that part. So let's look at what happens in method 2. So instead of this loop over k, we're going to grab this song ID and we're going to use the in operator. So basically we'll say in vector says this song ID in unique song IDs. So basically we're checking whether the current song ID in the jth row of the data set is a member of the song IDs we've already accounted for. So it's doing the same exact thing, but it's writing the code in a different way. We're using a built-in function or operator called in, as opposed to kind of basically coding in ourself in this loop. So another example where you should use kind of, if there's a built-in function to do what you want to do, that function is probably going to be better and faster than you coding it yourself like this. Okay, so let's run this. Okay, you see that finished a lot faster, 2,000 milliseconds, so it's 2 seconds as opposed to 17 seconds. And then now we can see what's taken a long time. So that's result 2 is method 2 going into the function. Now it's spending a lot of its time on subsetting the data set, and it's spending also a lot of time finding the rows of the data set that match the current song ID. And very little time here. So this is only 0.2 seconds. Okay, so now you might just declare, I'm done, this runs fast enough, and move on with my life. But actually you should check to make sure you got the right answer. So there's a couple of functions, and I encourage you to read the documentation for these two because they're not, they don't do exactly the same thing. But in this case, if we do identical result 1, result 2, that gives true. All.equal gives true. So everything is fine. Method 1 and method 2 give the same answer. So again, you might just decide, okay, this is fast enough. But you know, this is really on a smaller version of the data set. So on the big version of the full version of the data set, this might not be fast enough. So we got to keep going. And basically the strategy is look at these profiles, figure out what's taken a long time, and try to think about other ways you could do this calculation to eliminate the slowest parts. Okay, so let's take a look at our next method, method 3. Okay, so in method 2, we grabbed this here, and then we put these ins into subhot. So which, this returns a true-false vector, and which converts that to the indices that are true. But you can actually, instead of converting this to numeric indices, you can actually input just the true-false vector, and it should give the same thing. We saw in a video that that's not quite true because of missing values, but here there's no missing values, so that's fine. So that's all this does. Method 3 is just this without the which. So let's run that. And let's recall this one took about 2 seconds. By the way, these numbers aren't perfect, but they give you a general ballpark of how long things take. All right, let's do method 3. Okay, it's actually maybe a little bit worse. That didn't help. If we scroll down, this part actually takes a little bit longer. So maybe we don't pursue this. Let's look at method 4. What we're going to do in method 4 is, so here, we're going to convert the song ID. So the song ID, just to remind you, hot $song ID these are character strings. These are the first 10. They're all the same song. Perhaps if we convert them to be factors, things could run faster. Basically, factors, it converts a vector of character strings to basically assigns a number to each of them, and internally it's storing them as a number. So maybe doing numeric comparisons will be faster than doing string comparisons. So let's try that. Method 4. Okay, that took a long time, 51 seconds. When I ran it before, it took about 30 seconds. I wonder if the screen recording stuff is using computer resources, making things run even slower. But that's really bad. If we go down to the code, basically this is making everything worse. So doing this operation takes 14 seconds now. Doing this operation took 34 seconds. So this is like, makes things way worse. So maybe we can save this. So let's, oh, and it also, they're not identical. The reason for that is result $4 unique song IDs. These are now those numbers instead of the character strings. Okay, so let's look at method 5. So that was a failure. In method 5, we're going to fix one thing in method 4, basically this thing. And the way we do that is we keep track of this song ID. We keep track of the factor version. We're going to do the comparison using the song ID instead of the factor. And we'll do this comparison using the factor just so you can see. And at the end of the day, we're going to store the song ID, not the factor here. Okay, so let's run this. Okay, that's done. It ran a little faster because let's get down here. Because I fixed this part, so this ran faster because I'm using the character string instead of the factor. This is to show you that if you do these comparisons with the factor, it's actually much slower. I think what's going on is basically, even though this is stored as a number, it's still keeping around all the factor levels for all the other song IDs, and that overhead is really making this run very slow. Okay, but identical. This is true now because we're storing this song ID instead of the factor here. So we didn't actually get the wrong answer. It was just kind of returned in the wrong way. But converting to a factor doesn't really help. In fact, it makes it much worse. So let's go to method 6. What method 6 does is it does convert to a factor, but I do as.numeric afterwards, and basically that strips all the level information for the factor. So it really is just stored as a number. Down here, we're going to get the numeric song ID, and we'll still do this comparison, but we'll do this comparison using the numeric. But we're never doing the factor comparisons because we never actually have the factor version. Okay, so let's run method 6. Okay, this took 1.8 seconds. And are we working? Yeah, we're still working on the same data set. So this is actually our fastest one yet. If we go down to the code, it's basically the same two bottlenecks are showing up, but there's this additional one. This takes maybe a little bit more time than before. So we haven't really gotten much better. So we're going to have to think a bit harder. So let's look at, let's see. Okay, that's still the right answer. So you should be checking as you go that you're still getting the right answer. But we have gotten faster since our original one. So I'm going to give it a bigger data set and run that. while that's running, let me take you quickly to method 7. Because this is going to be a bit different. What's going to happen on method 7, we're going to take the full data set and call the split function. Basically what this does is it takes the data set and splits it up according to the unique song IDs. Okay, 6 is done. Let me take a look at that. So this took 24 seconds. Remember, this is a data set. 1E5 is 10 times bigger, so that's about right. Now kind of an interesting thing happens. Before in, let's go here, profile 7. All right, profile 7, this part, finding the indices, takes longer than this part, about double. Whereas in profile 6, subsetting takes longer than finding the indices. So this is what I mean by you should be trying this on the full dataset version because different bottlenecks may pop out depending on how big the problem is. Okay, so let's take a look at this. Okay, everything's running fine, but maybe this isn't fast enough for us. So we're gonna run method 7, which I introduced you to. And basically, I want just to show you how this works, I want to run it in debug mode. So I'm going to call it. So we're in method 7. This is the code I just showed you. There's head, hot. You can see that. So this split thing, it's running. And it's done. So let's look at split. So class split. Oh, sorry, class. That's the function. Split hot is a list. So we could do split hot 1. Basically, this is the rows of hot corresponding to this song ID. Okay, so you can see how this will be useful. Basically, we can now loop over the list split hot. It's already, done the operation of finding the rows of hot that match each song. Basically, I have all the data for each song in split up and split hot. And I can just look at the chart date and figure out which one is the first chart date and then grab the URL for that chart date. So let me just run through the rest of the function. Initializing first URL. There's the loop over split hot. So right now J is 1. And we just looked at split hot 1. Unique song IDs of J. So we're updating unique song IDs. The first one is going to be split hot J $song ID 1. So that's that one. And now we have to look at chart date and match all the chart dates in split hot to the minimum chart date. That'll tell us which row to grab the URL from. And then we get first URL is split hot J $chart date min in. So let me run through that. So the first row, if we look up here, the first row of split hot is the smaller chart date. And then, so we get 1 for min end. And then we grab the chart URL of the first one. Oh, actually, this is wrong. We have to get chart URL here. That's why you run it in debug mode. Okay. Now let's run that. Do that. Still in debug mode, so let's get out of here. Okay. source performance funds. Okay, so that was a big improvement because the previous one took 24 seconds, and now this is 3.6 seconds. Remember, this data set is 10 times bigger than the one we saw before. So this is like doing the previous problem in 0.36 seconds. So this took 3.68 seconds, and then we can start to look at the bottlenecks. Okay, this is interesting. So here, this is not showing up as yellow here. Basically, the R wasn't able to capture which line of the code this was happening in. I don't know why, it just didn't. But if you look over here, it was able to capture. So in reality, so I'm looking at method 7 here. Most of the time was spent here. And you can see that by saying split.dataframe was being called. However, it's not showing up here for whatever reason. And these operations are very fast. So so these operations are everything here, and the split is taking the most time. That's fine because overall it's much faster than not doing it this way. But now this is our bottleneck. All right, so again, you might decide 3.6 seconds for 100,000 rows is good enough. As long as I'm getting the right answer, that's fast enough for what I need, and I'll stop. So you may have better things to do than make this code run faster. But of course, there's going to be situations where it's really critical to make it run even faster. And so you'll keep going. So let's take a look at method 8. Let me close some of these up. All right, method 8. One of the issues is that in this part, because the data aren't in order, we have to, basically they're not ordered by date. We have to search for which is the first date. However, if they were ordered by date, we wouldn't have to do that part. So all method 8 does is it pre-sorts the data by date. So it figures out the order, then it pre-sorts the hot by that order. So now you have hot ORed. Then you do the split, and then you do the loop. So let's run that. Now, we don't expect this to have a big impact because most of the time is on the split, but let's run it anyway. I also put some print statements to see what was happening. This actually took longer. Why is that? Oh, interesting. Converting, let's go down here. So these operations that were required for doing the sort actually take a bit of time. So you may add code. So this, even though this isn't showing up here, it's showing up here. So this took over 1 second. So it takes some resources to convert a date, sort of a character string. The chart date is a character string to a date format. The reason we did that is so that we could sort by it. We'll come back to that in a minute. This is the split, so that still takes the majority of the time. But this part actually does run a bit faster, so we squeezed a little bit out of that part, but at the expense of taking too much time up here. Okay, so that's a bit of a failed excursion. Maybe we should just focus on the split part. And if you look at the code, hot has a whole bunch of variables in it, but in the code, only chart date, song ID, and chart URL get used. So maybe just don't pass it the full data set, just pass it those 3 variables, and that should just run faster on its own. I'm not running this one inside the profiler because we know what happens, but this makes the split run faster. So we went from 5.5 seconds to 2.6. So that did help. It basically more than a factor of 2. Okay, but maybe we need to go faster. Let's look at method 10. Oh, sorry, method 9. We're here. So the only thing different about method 9 is, okay, let me find it. 8 versus 9. So in 8, I do the split on the whole data set. So this is just, we're just passing it 3 variables. But in 9, I'm only doing it on those 2 variables because after we use the chart date to reorder things, we don't use the chart date anymore. So maybe we can squeeze a little more juice out by saying, okay, forget about chart date from now on. Just do the split on these 2 variables. All right, so let's run that. And it doesn't run faster, so that didn't really help. Let's time them both again. There is some variation to this timing. Okay, so that time it did run a little bit faster. So you should rerun things a few times. I think if you ran this a bunch of times, this second one would run a little bit faster, but it's not a game changer. All right, now let's look at method 10. Method 10 is quite a bit different. We convert the date to a date, that's fine. We reorder. And instead of doing the split, we're going to call a function called tapply. And let me show you how this works. Let me give ourselves some more room because this is kind of crowded. Tapply has 3 arguments. This is the variable we want to apply a function to. This is how we're going to split up this variable. And this is the function we're going to apply. So it's best to kind of read this as we're going to apply this function to this variable, but separately for each song ID. So this is going to work similarly to split. So basically we split up, when we use split, we split up the data set by this variable, and then we applied this function to this variable from the split data set to grab the first URL. And this just puts everything kind of just in one of these apply functions. Okay, so let's run this. So let me just repeat that because I think it's best to read this in this order. Apply this function to this variable separately for each unique value of this variable. Let's run method 10. Oh, and by the way, you're going to get slightly different times whether it's in the profiler or not the profiler, so be careful with that. All right, so this, even though we ran it in the profile, and generally that's slower, it's faster. This method is faster. If we go to the code, you can see that on this representation, it's spending most of its time converting the date string to a date object. And this is actually very fast, only 0.2 of a second to do that. Okay. Oh, and by the way, I didn't say this, but we're giving it now the full data set as opposed to a subsample. Okay, so that's running in 1.4 seconds. So again, you may decide 1.4 seconds is plenty fast. Let's move on with our lives. But maybe we need to go faster. Let's look at result 11 and see how that's different. Oh, by the way, I'm slightly cheating here. We're going to come back to this. We're just returning the URLs. We're going to come back to doing it right at the end. Okay, method 11. maybe we just shouldn't convert it to a date. If you look at hot $chart date, these are strings, but they're actually in a format that if you just sort them by like alphanumeric sorting of a string, you actually are sorting by date. So maybe we could just avoid this and just do the ordering by chart date and move on with our lives. So let's run this. Method 11. That was slower. Okay, why was that slower? Okay, so we didn't do this step, so that took 0 time. We did this step, so this took basically 2 seconds to order this, and then everything else was pretty fast. Let's look at the previous profile to compare. In this one, converting it to a date took a long time, but that actually was an overall benefit because after you convert it to a date, figuring out the ordering is very fast. As opposed to here, we didn't do the date, we didn't convert it to a date, but it actually wasn't worth it to not convert it to a date because if you try to do the sorting on character strings, it takes much longer. So even though we eliminated one step, that step was actually helping us in this step. It is worth it to convert it to a date first. Okay. So sometimes you learn things that you don't expect when you do the profiling. Let's see, result 12. So we're worrying a lot about this sorting thing. So what if we just tell our team, give us the data pre-sorted? How long does that take? So that's what we're doing in method 12. So I'm not counting this as part of the time. So maybe you just decide there's no reason why we can't get the data pre-sorted. So we shouldn't waste too much time here trying to optimize how we do the sort because we could just ask someone else to give us the data pre-sorted. So just to see how long that takes, that's less than 1/4 of a second. And for most purposes, that's going to be plenty fast. Let's look at 13. This is a completely different method. There's a really useful function called duplicated. And what it does is you take a vector, song ID. Actually, let's run this in debug mode so I can show you. Okay, so like we said, method 12, we're assuming hot is already ordered. So we have hot, so head, hot. These are the oldest songs, 1958. And, oh, sorry, we're doing the wrong one. We need to do method 13. Debug. Method 13. Again, we're already assuming it's ordered. All right, so we have hot $song ID. Okay, those are the earliest songs. If we run this line, so first of all, dupes 110. These are all false. The reason they're false is because there isn't a row of the data set that matches this that came before it. So obviously that's going to be false for the first one because there are no rows of the data set. But if this one matched one that came before, then this would be true, meaning that it is duplicated. So let's actually give this an easier problem so that you can see how this works. Okay, so we're giving it 1, 2, 3, 1, 2, 6. So it should return false, 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 true because 1 happened already in the vector, true because 2 happened already, then false. False, 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 true, true, false. Okay, so that's what duplicated does. So once we have duplicated, basically all I'm going to do to get the first URL for each song is to get the ones that are not duplicated. So meaning it leaves out the duplicated ones. And that should give us all of the first URLs. And this will run very fast. And then we also grab the unique song IDs from those same entries. That also runs very fast. And then we return. All right, so let's time that one. Okay, that's like wicked fast. 0.017 seconds. Okay, so now we've actually discovered something kind of interesting. We thought 1/4 of a second was good. This is more than 10 times faster than that. Okay, let's look at number 14. So we kind of cheated here because we assumed it was already ordered. If you don't assume it's ordered, you can actually just reorder it in the function. So let's see how long that takes. So this is the same as 13, except we're doing the reordering. This will obviously take more time, 1.3 seconds. And all right, now I want to focus on this ordering because that's what's taking all the time. And let's look at this very last method, method 15. So the sorting is faster when you convert the string date to a date object. That's because internally the date object is storing things as a number, and then it's easier to sort numbers than it is to sort character strings. Okay, but can we convert it to a number for the purpose of sorting without converting it to a date? Because there's a lot of overhead. There's all kinds of other information that gets stored with the date object, as opposed to just the the numeric day number. So here's my attempt to do that. So what I'm going to do is on chart.date, I'm going to call gsub. And just to remind you, hot dollar chart date. That's what these look like. These are just character strings. Basically what I want to do is remove these 2 dashes. So it's just going to be the string 1990-0505. And then convert that to a number. That conversion should be pretty fast because these are all nicely formatted as digits. And then we'll have year, month, day as a string. When we convert it to a number, it'll be a number. And if you sort those numbers, it should give you the right ordering because year is the biggest division. It's kind of like it's the year column. Month is the next biggest, and then day is the most refined. So as long as it's in that order, if you convert it to numeric, it should give you the right answer. So this is similar to converting it to a date, but converting it to like a date object. But this is kind of bypassing all the overhead that comes with that by just getting the essentials of what we need. As we said before, this follows that principle of don't do more work than you need to do. Use the simplest method. You might say this is more complicated in terms of the code, what the code looks like, but if you look at the as.date function, that function is much more complicated than what's actually happening here. Okay, so let's run method 15. And that runs very fast, 0.326 seconds, and it's not assuming that the data are pre-sorted. So this is probably the best we have. Maybe you can figure out how to do it faster, but this is fast enough for me, so this is the point at which I'm going to quit trying to optimize this. Okay, so general principles: use the simplest object for the job, use the simplest function for the job, time things, figure out where the bottlenecks are, think about other algorithms you could use. In this case, it turns out that using duplicated was the fastest way to do it. Experiment, retime things. Often what you find when you profile the code is that the thing that you thought would take a long time is actually not the thing that's taking a long time. So that allows you to not waste effort optimizing things that actually aren't the problem. So it's really important to time your code. And then have fun. I find kind of this optimization stuff fun to work on. So you may too as well. Okay, that's the end of the video. Thank you.